Alright, our next topic is convective heat transfer for the cylinder in cross flow. So we are going to focus on cylinder in cross flow. So as in the previous case, we are interested in finding the local and average convective heat transfer coefficients. The average one will depend only on Reynolds number and Prandtl number. The local one will depend on the position. The average will only depend on Reynolds number and Prandtl number. And likewise, we are also interested in knowing the drag coefficient. It is a function of Reynolds number and the position. So now, let's take a look at the flow behavior around the cylinder, an immobilized cylinder, and there is fluid flowing towards it. And this fluid has fluorescence dye in it to make the flow behavior more clear. So I would like you to pay attention to the streamlines around the cylinder, in particular very next to one. So I want you to understand at what point the fluid basically grabbing this cylinder and at what point the fluid layer is detaching from or separating from the cylinder. So that is one observation. So this is another video. This shows a computational model of fluid coming towards a stationary cylinder, and the velocity magnitudes of the velocities are shown in the color here. The red means high velocity, blue means low velocity. So as you can see, the velocity at the front is almost zero because the fluid is coming vertically towards the tip of the cylinder. So that's basically, it's an obstacle. It's like basically it is stopping the fluid to go any further in X direction. And then eventually there will be some fluid that is following the contour of the cylinder, and then it is going to gradually increase and increase, and eventually you will reach a maximum. At this maximum, the fluid will start to separate. It is not going to go back, grab the cylinder, but it's going to basically separate, and it is going to create a wake. Okay? So that's the main observation from this computational model. So as you can imagine, whenever there is a variation in velocity, there will be a variation in convective heat transfer coefficient. So now, before we go into actual convective heat transfer coefficient, let's just summarize some of the observations that we saw from the videos. So one of the observations that we have, there is a stagnation point at the front. So basically, when the fluid comes directly towards the tip of the cylinder, it is going to stop because it is like a barrier. It will not be pushed. And then you will have a laminar flow forming around the cylinder. It's going to continue, and eventually this laminar flow is going to separate. And after the separation, you will have turbulent region. We call this region as wake. Okay? So the angle at which you see the separation is important. So I want you to pay attention to this, and I'm going to explain it further in the next slide. So depending on the Reynolds number, this angle of separation changes. So if the Reynolds number is less than 5 times 10 to the 5, then the separation happens around an angle of 80 degrees. When the Reynolds number is greater than 5 times 10 to the 5, separation is delayed, and it happens at 140 degrees. So what does it mean? Just think about you have a viscous material. You are trying to increase velocity. So Reynolds number is directly proportional to velocity. So let's say in the top case, we have a small velocity. That means the fluid is not going to be forced to conform and grab on the cylinder. So that means it is going to partially grab only at the front part, and only going to conform on this geometry on the front part. However, when the velocity is very high, it's going to push the fluid further down. It's going to force fluid to conform more, and it's going to create a separation at larger angles. So that is the idea. And usually you can see here separation. So we have a transition. So we started laminar flow, and then we'll transition into transition flow and then turbulent flow, and then you have the separation. So if you would like to calculate the drag coefficient, so the drag coefficient can be written in terms of Reynolds number. So if V here is the velocity, D is diameter of the cylinder. So diameter of the cylinder, nu is the kinematic viscosity of the fluid. Okay, so what you do, you calculate the Reynolds number and then you read it from this graph. And right now we are talking about cylinder, and you can also use this graph for sphere as well, but let's focus for now on the cylinder. Okay, so again here the angles are shown in here. So if the Reynolds number is less than, let's say, 1, there will be no separation. Okay, and when the Reynolds number is greater than 2 times 10 to the 5, the separation happens at 140, and in between this separation happens at 80 degrees. So you can easily calculate the drag coefficient, which is defined as the drag force divided by area divided by rho v square over 2. So as you can imagine, the Nusselt number, which is the indicative of the local heat transfer coefficient, varies very non-linearly. So it depends on the angle, because the velocity changes with angle. So depending on the Reynolds number, we may get different trends. So what you need to do here, so if you are interested in, let's say this is the angle, let's say if you want to calculate the local Nusselt number here, H local, at 90 degrees, so you read the graph, you calculate the Reynolds number, and then you read y-axis here. And after you have the y-axis, so you need to look up Reynolds number and Prandtl number again, and then back calculate Nusselt number. From there you'll calculate H. So there are also other equations. So if you don't like to use the graphs to read the values, so there are empirical equations. So one of these equations is called Hilbert correlation. In this correlation, we have 3 variables. So we actually have 2 variables, C and M. Okay, so the Nusselt number, this is average Nusselt number, which will give us the average convective heat transfer coefficient, will be a function of Reynolds number and Prandtl number. And then we have 2 parameters that we need to read. And the values of these parameters will depend on the Reynolds number. So there is a table in your textbook, it summarizes the C and M values for different Reynolds number. So you basically read your Reynolds number first, and then read your C and M, and then calculate the Nusselt number, and from there you calculate the convective heat transfer coefficient. So, and again, the properties are evaluated at TF. This is extremely important. So you need to evaluate the properties at T film. So T film means Ts, the surface temperature, plus T infinity over 2. Okay? So that is important to realize. So far, all of the equations that we have discussed evaluate the properties at T film. Okay? So, and what happens if you have a cross flow, but in this, instead of a cylinder, we have a different shape. Let's say you have a square, diagonally oriented, or in perpendicularly oriented. So you will have different C and M values. These are tabulated again in your textbook, and you can also read it from here as well. So you just need to identify if you have a different non-cylindrical rod geometry with a cross flow, then you just use this graph to find C and M values. Again, properties are evaluated at T film. So there is another equation. This is called the Zukaskas equation. This is, in this case, we have, again, everything is function of Reynolds number and Prandtl number, and we have 3 variables here. So depending on the magnitude of the Prandtl number, we have a different n value. They are slightly different. And C and M values are dependent upon the Reynolds number. So I want you to pay special attention here. So everything, all the properties here are evaluated at T-film, fluid temperature. This is extremely important. If you are using the Dukaskas equation, properties, Reynolds number, Prandtl number, will be evaluated at the fluid temperature. However, PRS is evaluated at the surface temperature. So in a way, you are considering the effect of surface and fluid in this term, but everything else here, everything is written here. If there is no subscript, they are evaluated at the fluid temperature. Again, this equation is slightly more complicated, but slightly more accurate. So again, so you need to also remember the validity of the equations. So this is valid as long as Prandtl number is greater than 0.7. This equation has two components, and the validity is given in here. Okay. So there is another equation. This is called Churchill and Bernstein correlation. In this case, we have a much more complicated equation. However, we don't need to use the tables to find C and M values. Everything is given in terms of Reynolds number and Prandtl number, and everything is evaluated at film temperature. Okay, everything is evaluated, all the Reynolds number and Prandtl number will be evaluated at film temperature. So also, I mean, for the sake of saving time in the exams, so you may want to create functions in your calculator, or if you are going to use Excel, I'm going to allow that. You can create these functions, or MATLAB, you can create these functions. So you can try to create a Nusselt function. So let's say it will be function of Reynolds and Prandtl number. So you can create two variable functions, or you can even use Mathematica if you like, to be able to basically minimize the amount of error and save time. So you can create these functions. Maybe it could be a good exercise for you when you are solving the homework. Try to create these functions in your software or calculators. So now we are going to solve an example. Let's take a look at this. So we have a long cylinder and the diameter is 0.1 meter, and there is a wind blowing around this in cross flow geometry. So the velocity of the wind is given, the temperature of the wind is given, 10 degrees Celsius, velocity is 8 meters per second, and the rod is at 110 degrees Celsius. We are asked to find what is the rate of heat loss. So to find the rate of heat loss, we need to know H. So basically we need to calculate H, and from there we'll calculate Q loss. So that will be the idea. So let's do this analysis now. Okay, so let's do that. So this is example. Cooling of cylinder with air. So let's start to list what we know. What are the known? So the knowns are, we know the surface temperature, we know the fluid temperature, we know the velocity of the fluid, and we know the geometry of the problem. This is a cylinder, as we mentioned multiple times. Our goal is find Q convection. So that requires actually H average. So we'll assume this is a steady state process. We'll assume radiation is negligible. We'll assume that air is ideal gas. Okay. So now let's move on to the analysis. So for a cylinder, if we go back to our slides, we talk about three different equations. So we have Churchill and Bernstein equation, which use T-film. So we have Dukaskas equation, which use T infinity. And then we have Hilbert correlation, which uses T-film. So ultimately, I need to choose one of these, and as long as the range criteria is satisfied, I can use any of these. Since two of the equations depends on T-film, I would like to just start to calculate T-film. So this is Ts minus T infinity over 2, which is 110 for the surface, 10 degrees for air. So the average is 60 degrees Celsius, which corresponds to 333 Kelvin. So at this temperature, thermal conductivity of air, I need to look these up. Okay, so you need to check your at the end of your textbook, you need to look up these properties, and this one of the most important part of this analysis in chapter 7 to be able to read values correctly. So thermal conductivity is 0.028. Kinematic viscosity is 18.96 times 10 to the minus 6 meter per second. And the Prandtl number is 0.7202. Okay? So now we have the properties. So now I would like to calculate the Reynolds number. The Reynolds number will depend on incoming velocity times diameter divided by kinematic viscosity. And the air was at velocity of 8 meters per second. The diameter of the cylinder was 0.1 meter. The kinematic viscosity is 18.96 times 10 to the minus 6. So we'll get 4.2 times 10 to the 4. So this is the Reynolds number. So now let's go back to equations again. So we have, so let's see. So we have equation, Churchill and Burston equation that requires the product of Prandtl number and Reynolds number is greater than 0.2. So in here, so the Reynolds number is 4 times 10 to the 4. The Prandtl number is 0.7. So this will be satisfied. So why don't we start with this equation? So let's use this equation actually. So now we will use Churchill and Bernstein equation. Okay, so the Nusselt number, the average Nusselt number, is H times D over K fluid. So the equation was 0.3 plus 0.62 Reynolds number to the 1/2 Prandtl number to the 1/3 divided by 1 plus 0.4 over Prandtl number to the 2/3 power to the 1/4 power times 1 plus Reynolds number D over 282,000 to the 5/8 and everything to the 4/5 power. So here it is just a substitution equation. So we will be substituting 4.2 times 10 to the 4 for Reynolds number. 4.2 times 10 to the 4. For the Prandtl number we have 0.7202. And then we will evaluate this. And after you carry out the algebra, you get H times D over Kf is equal to 124. So that means H bar is equal to K over D, K fluid over D, times Nusselt number. And K fluid is 0.02808 watt meter per Kelvin. The Nusselt number is 124. Diameter is 0.1. So we get 34.8 watt meter square per Kelvin. Okay, so this is H. And if you are interested in calculating the convective heat transfer, rate of heat transfer, Q convection, which is H, A surface, Ts minus T infinity. So H average, and A surface is pi dl for a cylinder, and Ts minus T infinity. So here we have 110 versus 10. H is 34.8 and pi dl is pi, diameter is 0.1, L is, let's say, 1 meter. So we will get 1093 watt. Okay, so this is the rate of heat loss from a cylindrical object.